Okay, so welcome to module 12. This will be one where we look at the research and on the reporting on real-world model-based testing. So what's been used in different industries and show some examples of how. And the focus here is going to be, as you will see, a lot on UML, because that's where a lot of the industrial model-based testing is based. But in this video, I'll show an overview of what's out there, what's being used, and I will show some examples which are not UML based primarily. So TTCN3 is one example. It's a language for testing from the telecom domain, and you need to know about it because of its historical importance. And then I'll show a sort of a modern variant based on behavioral driven development, or BDD, or behavior driven testing with Cucumber and the connection to model based testing. And then probably so that this video is not too long, I'll split up and do UML, a very recent example of UML based model based testing on a very interesting recent paper. Okay, so overview and a few other examples in this one, and then a little bit more focus on a UML based one in the next one. So let's get started. UML and real world model based testing. So the main question for today is which MBT models, testing tools, and so on is used in industry. So you've seen one type, you've seen one type of MBT now in John's lectures, videos, and the assignment, and we discussed Simulink a little bit, which is a major one. But what else is out there? So different types of model-based testing in use and mapping. Can we see some connection between different types being used in different domains? So here's a quite interesting paper from 2012, which still stands in a sense. It's a taxonomy, an overview with different criteria, different ways of looking at model-based testing and approaches. And you can see, so this is from the paper of Utting et al. 2012. So this is part of the course material. And as you can see here, they divide it into model specification on top. So this is how do you write down the model, and what is the model about? What kind of expressions? What does it include? What can it express in a sense, right? So you have scope there. So what is being modeled? Characteristics. So what can be expressed in the model, a specification, the modeling language you use. And then specific paradigms are specific techniques or ways of specifying models. Another top category in this taxonomy is then you go on to test generation. So you need a model, which we discussed in this course, right? And then from that, you're going to generate test cases or generate some other test artifact for that matter. And so this is part of the test generation in this taxonomy. And as we discussed, you need some criteria. So something that measures what you want to achieve when generating tests. And typically these are some kind of coverage criteria, right? So that is discussed in test selection criteria in this taxonomy. So there you can have structural model coverage. So this will be, for example, what we saw on Simulink. So can we cover specific edge transitions between nodes or specific nodes if we have a graphical model or a finite state machine or something like that. But there are other possible selection criteria like data coverage. So if you have a model of the data input-output domain, you can try to cover that in different partitions or different sets of that and so on. Diversity-based techniques are very recent and something that I've been working a lot on. That's not mentioned here because it's been more in prominence in later years. You can cover requirements, specifications of other sorts. Random testing is of course very prominent and important, and then fault-based, which would focus on earlier faults that you've seen for this system or for similar systems and so on. The taxonomy also covers technology for test generation, so random generation, search-based testing, which we'll come back to. Model checking we'll not discuss in this course. Maybe you've seen it in other courses or will see. Symbolic execution and the same there, theory proving. So many of these techniques are more formal and they can give you guarantees in some way. Of course, the guarantee is always in relation to the model. So if the model is not very fine-grained or high resolution, then your guarantees will not be fine-grained enough, typically. But it depends. And then third part of the taxonomy, which is maybe the least interesting, is test execution. So it's very important that you understand after this course that automated testing is not so much about test automation, automated execution. It's about automating the good creation of good test cases, right? Or to derive good test cases from artifacts that you have during development. But of course, test execution is also important, and especially in industry, this can be a major cost, so it has to be part of this taxonomy. So yeah, when it comes to paradigms, the pre, post, or input domains, they are typically more formal approaches there. So there are languages like B and Z. They've been used in train safety software, especially in French. So in France, in Bombardier and others, they have a tradition in France and in Canada, in French Canada, of strong companies doing well-known products in the train area. So there's been a lot of focus on B and Z and these type of languages. But also in aerospace, so Boeing and others have used these type of languages. OCL is part of UML and often used together in UML models, so that is quite prominent and something we'll get back to in the next video. And that's about the transitions in a UML model, or about input domains and different dependencies between events and input and output domains. Finite state machines that you've seen in the previous lectures and in the assignment, or that type of modeling is the basis for a lot of model-based testing, right? So often it's like transition-based. So you want to somehow ensure that you cover different paths and cover different transitions in those models. History-based is a different one. Let's not go into details there. Algebraic specification, so you can get more and more formal here in writing more mathematical looking models and descriptions. They can describe the functions from a black box perspective, so to speak. Operational, there are models, Petri nets. They are basically FSMs with the timing of events in the model itself. So you can express that things need to synchronize or can divide in time and so on. So they add something on top of the traditional FSMs. Stochastic, so they somehow use chance or randomness. Markov chains, Gödel test is our own tool or approach implemented in our tools, which is search based. So it's basically you don't get guarantees, but in practice these approaches can help you find a lot of good test cases in a fairly short amount of time, but they sacrifice the guarantee there. And then data flow. So Simulink is mainly a data flow modeling language. So it's about how data flows in the computation and what the different nodes are transformations on the data. So there you see some of the different paradigms. So if we look again at the taxonomy on the left here, you can link that to an overall general process model for model-based testing or process overview. So model specification is about how do we express the requirements, our understanding of what the system needs to do in some type of model, right? So this model will severely sort of determine what you can do with model-based testing. because the model is the basis for all the other steps, right? Test selection criteria are then used based on the model or from the requirement somehow. So from this first box, we can get test case specifications, but this can also happen purely from requirements. So here it depends a little bit about how you see it, right? But test selection criteria can be model based on the model itself or more related to the requirements. So we have more general criteria that we want to fulfill with our testing. And this is then expressed in a test case specification or a test specification. A test plan is often what they call it in the industry there. So, for example, if you are following a standard, then that will tell you from very general perspective that you need to fulfill. You need to model in this way. You need to show coverage of the model or of the requirements in a certain way. Then comes to the test generation technology, and that's where it comes together. So you take the model, you have specific goals, so you have criteria, and now you can use the model to create test cases or some other test artifact to fulfill these criteria. And then finally, test execution in some sense is the least interesting, but the most interesting here is what is your oracle, in a sense of what will determine what is the correct behavior, because much model-based testing cannot do that. It can only generate good test cases. We will look now in assignment 3, you will work a little bit with property-based testing, and in the next module I'll talk about that, so you get a good start there on the assignment. And property-based testing, there you get the verdicts by writing specific functions that express the expectations you have on the software under test. So this gives a good overall understanding of the field and a taxonomy for how to view things. So if we take just one example of this from this Utting paper, they then go through specific techniques, paradigms and tools. So here is one example of the Microsoft Spec Explorer. So this was developed within Microsoft Research during the last 7 years. So this was published in 2012. So this was from 2005 to 2012. And it was used a lot in Microsoft in that day. I haven't asked them recently, actually. I should. I think it's more limited use nowadays, but maybe in some teams they use it more. And they also integrate some of this in their development tools. And this Spec Explorer provides model editing composition, so take different sub models and compose them, put them together into a larger model for a larger system. You can explore these models, you can sort of visually go through them. You can have automatic exploration and so on to help understand what does this model lead to, and also visualization then is part of exploration to show the model and its effect and sense. And then the tool Spec Explorer can generate offline.net test suites or execute test as they are generated online. So offline means we generate basically files with the test cases here for Microsoft.NET, of course, because it's a Microsoft tool. Or the tool itself can sort of online run test cases. And the online one is, in some sense, has benefits, because then you can select new test cases based on the results of the previous ones. Of course, the offline test generation is better for ensuring that you run a certain set of test cases again and again. So it depends on the use case here. Both ways, I mean, many tools can do both things. Other examples of commercial MBT tools that use these type of behavioral test models are Qtronic from Conformic and Certified from Smart Testing. So yeah, these are, I don't know these tools, but they are basically similar. So what's the scope of the model? From the taxonomy, we can analyze an MBT tool like this. First we look at the scope of the model. So what can it express and what is it focused on? So Spec Explorer has an input model where the focused model where the soot is seen as an input output. So we don't go in and look too much into the internal. So this is more of a black box input output model, and it's composed from simpler models, and the model also allows you to provide oracles. So not only can it generate test cases, you can also express what to expect from running those test cases. So preconditions are associated with action methods of C# models, can be used to model some environmental assumptions. So yeah. So as you see, I mean, many of these things, you see the same elements. So there's some graphical language, or there's some formal language which can be represented in graphical form, which is typically some extension of FSMs. So express what the nodes are, express transitions, and then you have some kind of logic or language to express what goes on for transitioning between different nodes. And here the focus is black box. You're not going to see individual internal steps. It's going to be focused on sort of the external view of what the system should be doing and the states it should be in. So model characteristics. The models are untimed, so there's no way to express that something should happen before others or after and so on, or intervals of time. And the models are discrete, so you can basically step through time in logical discrete steps. So there's no continuous time model. So continuous time is more often critical when it comes to embedded systems, because they have to react in continuous time as things happen. You can sort of stop the clock and analyze what's going on and take discrete steps when you model these systems. But here, Microsoft Spec Explorer is sort of a desktop development tool. It's not for embedded systems per se. So here, Microsoft supports untimed discrete models. Non-determinism is supported by distinguishing controllable actions from observable actions. The latter may be generated spontaneously by the soot. So there's some way that you can model that things can happen, be triggered by the outside world, right? So this is non-determinism from the system. So determinism means that we know exactly what the next state should be, right? But in non-deterministic models, there can be an outside arrow coming into a state, and this is triggered by something outside of the system, like a sensor, another system sending us data, or some timing and so on, right? So this is timing in a sense. It's different from, you cannot express timing in the model, but you can have sort of random events or things that are triggered by a clock in a sense. So it comes from the outside into our model. So this is the characteristics of the model, the modeling paradigm, state-based models. So this is very close to what you've seen with the EFSM and FSM-based model-based testing. Written in C#, so they use the same language they are focused on testing. This is often good, so it's easier for developers and testers to use the same tooling and the same language and so on. So basically you can express logical expressions in C# in your model and somehow to constrain the transitions and so on. And then a regular expression notation is used to specify history-based, trace-based models and scenarios. So I'm not sure. I would have to look in more detail at this tool to see what that means. So regular expressions is often a way to express matching of strings. So I guess history here can be some kind of trace and log, and you can express things, trigger things based on things from the log or history. So that's a different way of getting a transition sort of from our own history rather than from some sensor or timer or external system. The C# models can have internal state. Yes, this is often needed for any type of complexity. They can have parameterized methods with complex parameters. Yes, since it's embedded in C#, this is to be expected. So you can basically use a big part of C# expressions to say and variables in a sense in your to describe your transitions or conditions in the model. Multiple models written in these notations are composed to obtain the final set model. This is often needed in more complex scenarios, right? Test selection criteria, so data coverage of parameter values, structural model criteria such as covering all transitions. So you see again, it's the same patterns, it's the same ideas that you've seen now in several of our modules. It goes again in most of the practical work on model-based testing. A regular expression can also be used as an explicit test case specification. When it is composed with a general C# model of a soot, it can restrict the general test to focus on that scenario. So basically for expressing a certain subset of data or inputs, for example, that you want to focus on. Like a kind of filter on the data that you want to test. Technology, it uses algorithms similar to bounded model checking. So this is how it's implemented to explore the model and generate tests. Yes, so this is kind of standard. In more formal models, you can use more formal approaches to create test cases, and supports both online and offline actual test execution. So here you see the use of this taxonomy, and with this in your head, and recognizing what you've already seen in the course, you can understand a lot of different MBT tools and technologies when you come out into practice. So this is an important way of structuring your knowledge. Of course, as time goes on, there will be slight new ideas added, things that might not fit perfectly with this model, but for sure you don't need to be feel that some new tool is very hard to understand. You can relate back to this taxonomy in your head and understand the basics of new MBT tools and automated testing tools. Okay, I looked a little bit into a more recent systematic mapping study on MBT tools and models. So we don't need to look into details here, but this gives a good overview. So here is what they found. So they looked into a lot of model-based testing tools and research, and basically they divided this into three main sets. So you have UML based on top there in green, 17 of them. You have formal models of some other sort. So these can be FSMs, EFSMs. The one we discussed from Microsoft would be formal in a sense, or other, and other is the third category here. But it's not UML based per se, it's some other type of model, right? So that was basically other is the other stuff that they couldn't fit into the two main categories, which is some type of more formal model or UML, which was the biggest single technique in a sense. And here you see that there are some crossovers, so things that are sort of categorized as both. UML plus formal method in a sense was 3 of them, and so on. But we will just look into some of these main categories. If we look at the main centers, there was a lot from Microsoft Research, and then there was a lot from German different corporations or also universities, but for sure there are quite a few North American universities here. There's one in Tampere, is in Finland, University of Paderborn, Munich, so you see some French, Fraunhofer also German, Carleton is Canada, Twente is Netherlands. So you see France, Netherlands, primarily Germany, France in Europe, and then US, quite a few both universities and research companies or research departments of companies. If we look at the map, we can see Germany in small there on the right is very heavily involved, but you also have the Seattle area, so around Boeing. There's been a lot in the aerospace industry. but also of course California and around Pentagon, Washington DC, and those states on the east, east coast of US, yes, and also Canada. You see on the world map there, Finland, France, UK, Germany. Okay. This one is a little bit complex. We don't need to understand all the details, but this is a so-called bubble graph. So you have a few things going on here. Start with the y-axis. There you have domains. So you have ATM would be banking applications, automotive, critical systems in general. So this can be some kind of safety critical and so on. You have telecom if you go down. So on the y-axis you have these things, and then you have on the positive x-axis, to the right of the y-axis, you have testing levels. So you see integration testing, system testing, regression testing, and acceptance testing. And you see by far then that there are the most bubbles on system testing. So you can see model-based testing technology is mainly used on the system testing level, right? Sometimes it can go down to integration level, and regression testing scenarios is of course sort of a different way to cut it, but you don't see any unit testing going on here. But of course this depends, right? Because if you're modeling the data, then in some sense you can be using it on unit testing level. So it depends a little bit on how you define things here. Then on the left of the y-axis you have just publication year. So this is a time-based axis. And there you see quite a lot of focus from 11 to 15, say, 11 to 14, then a slight downtrend, but this was done in 16, so you don't know if you can trust 15 and 16 years there. So some increase over the years at least. If we look, here's a similar structured graph, bubble graph, but here on the y-axis you have the different model-based testing activities. So you have what have the papers or tools been focused on. So model transformation, test modeling, test case generation, and here you see the most bubbles. So test case generation is in focus, then the test modeling itself, and then less on other things like test oracles, test data generation, and so on. The numbers here are the numbers of the papers. So in the reference list, not the total number, right? So 72 for test oracle in the approach is a single paper here or tool, not 72 papers, right? So the size of the bubble is the number of entries. So you see contribution types is approaches. So they describe a certain technique or way of doing test case generation in this large bubble here in the middle. And on the left you have research types. You see a lot of focus on empirical study and then industrial experience, not so much on experiments or proofs of concepts or theoretical work. Okay, that's an overview. If we look at the three main categories, you have UML on the left, and you see it's a shorter list, but there are quite a few references there. Formal methods, many different ones. So here it depends what do you mean with formal, but you see the B language we discussed. EFSM, you see a lot of activity, and FSM, these are the biggest ones, the ones you've seen also in from Jan and in the assignment. LTS is a time-based model, so quite a lot of that, and you need that for embedded systems and so on. And then other are, okay, it looks like a lot, but it's basically a single paper or two on a few different techniques, so you know, less focused on that category actually. Yeah, I already discussed those. You see Simulink, I forgot to mention Simulink, of course. EFSM, FSM, labeled transition systems, I think LTS can be used for time-based modeling. So there's a quite famous tool from Sweden, from Uppsala, called Uppal, or not only from Uppsala, but they contributed, which can do LTS. Simulink, so you see we have covered a lot of ground. when we discussed EFSM, FSMs, Simulink, and those other Petri nets and LTS and so on are more for specific domains and often see less use. TTCN3 I'll tell you a little bit more about. So TTCN3 is prominent, especially here in Sweden, because Ericsson used that a lot. It is a bit dated, so it's still used, but I would say in the industry at large, there's less focus on TTCN3 today. So it comes from telecom, and I guess the 90s was the main heyday, so it sounds very old now. But there are still many companies developing TTCN3 tools and doing work on this. I linked to some further introduction here, and I've used some of these slides here from someone else, but we're going to go through this very quickly. So TTCN3 is originally called a tree and tabular combined notation. So the idea was, probably from the 80s or even earlier, was that people were using either tree-based models or using tables to write down their modeling of telecom systems or this type of communication-based systems. So this was developed, versions 1 and 2, from 84 and onwards into the 90s. And then they updated it, they had standard bodies working on it and so on. And version 3 then was released at the end of the 90s, so about 20 years ago. So the main capabilities, it's a dynamic concurrent testing configuration. So these type of systems are like communication servers. They take in a lot of requests from a network, can be sort of like an internet router, or it nowadays can be like a mobile network router. And so they take in traffic from many incoming nodes, and they want to send that along and possibly doing some processing on it. So this means there's a lot of real-time requirements. Things are going on in parallel. You have concurrent testing of these fairly complex systems. So that's the focus of TTC, and because of its history, that's what it's focused on. Of course, you need to support different types of communication, so synchronous, where you need to synchronize and acknowledge, or asynchronous, where it's basically in a queue and then processed as you go along. And you can express this also then in your testing models. Data and signature templates with powerful matching. So this is basically how you express the type of data. So it's very tied to protocols. You have basic types, and you can put together these basic types and sets into protocols that will then be sent and parsed and generated for testing these systems. Specification of encoding information. Let's leave this for now. There are details here we don't need to go into. Display and user-defined attributes. So you can sort of, on top of the basic logical or graph-based models themselves, you can also specify how you want this to be presented, in what order, and at what level of granularity, and so on. And then you can test suite parameters. You can have parameters to express your test case generation. So basically this means you can generate a lot of different data and events to test these type of systems. You can have test case control and selection mechanisms, so some kind of conditions of what will happen when a certain data is sent and so on. And you can express and check test verdicts, or Oracle functionality. And this is harmonized with a communication standard or older standards here. It's not so important for us. And then a major thing here is that you can present the same model in different ways. And this was often sold as sort of the main thing here. Well-defined syntax, static semantics, and operational semantics. So it's sort of formally described, so tools can, at least in theory, interoperate. You can use different tools from different vendors, and they should be able to comply with each other and exchange information and so on. The core format is a text-based language, but it's formally defined how you can view this in other presentation formats, like tabular format for conformance testing, message sequence charts for better visual overview, and so on. So yeah, I mean, this is pretty basic stuff nowadays, but it was important at the time because of what people were used to and so on. It looks a bit weird maybe from our modern perspective, but it's like any simplified programming language where you have basic types of data and you express what to send over channels, alternative ways to handle incoming signals, and so on. And then you can check for specific verdicts, so you can set a verdict on when this test case is run. So you don't need to understand the details here, you need to understand what type of things is this, and what type of things can be expressed. So you can imagine nowadays that we would write this in the programming language that we use, but in some industries this is a benefit of having this independent format. Then you can take the same test case that was described in text and you can show this somehow in a table, a tabular format. So yeah, I can imagine this gets fairly complex even for quite small test cases or the models. And then you can also map this to message sequence charts, which is similar to UML sequence charts, because UML sequence charts sort of took some of the things from MSC. And here you can see sort of what are the different actors or systems involved, and there's an ordering in time, so time flows down basically, and things are ordered, and you can express acknowledgements and messages being sent between different subsystems or different systems. Yeah, you have generic built-in, you have data types, atomic data types built in, but then you can put together new data types like protocols and stuff that will be sent on these systems, and so on. So yes, this is major elements. You have data type, you can then use that to compose test data descriptions. You can describe the architecture, so what are the different subsystems and what kind of test data or data do they exchange, and then you can express behavior that you expect should happen. Okay, so that was TTCN3 in 5 minutes hopefully. So dated but good for you to know, and a lot of formal modeling approaches have similar attributes. So in the other testing category, I'm just going to show Cucumber, a behavior-driven technology here, because it has some interesting comments. So this is a paper about a tool called Skyfire, model-based testing with Cucumber, which is a BDD tool, so behavior-driven development tool, written in Ruby, which is the underlying language, but it has found use in also testing of other systems. And the behavior-driven development is basically that you want to write what the system should do, how it should behave, in a very high level. So Ruby is kind of high level, flexible typing and so on. So you can fairly shortly describe simple logical statements and things that should happen in sequence. And this is the idea behind BDD tools, is that even non-programmers or non-testers, so people, maybe a technically minded user or an analyst in your company, a requirements analyst, can write down something which can more directly be mapped to a test case. This is the idea. And here they want to bridge between the BDD thing, which is not model-based testing per se, wasn't conceived as a model-based testing technology. It was conceived as a testing tool, BDD, for automated testing and bridging the gap between requirements, so high-level expressions of what the system should do, and low-level test code. That's what BDD was. Here they present Skyfire, which is a way to bridge model-based testing with the Cucumber BDD. So Skyfire can automatically generate effective cucumber test scenarios to replace manually generated ones, right? So Skyfire reads a behavioral UML diagram. So it input to this tool is a UML diagram, a state machine diagram. So it will be similar to what you've seen in the assignments and previous lectures. The tool Skyfire then take this behavioral UML diagram and it identifies the necessary elements. It transitions on that diagram, and then it generates effective tests to satisfy various graph coverage criteria and converts those tests into cucumber scenarios, right? So it takes UML, it analyzes that, it has the normal graph related coverage criteria, and then it generates BDD, cucumber statements to cover this UML model. So this is a technology to bridge between UML-based, models to model-based testing. So it automatically translates the UML model to cucumber testing. And then, as in normal cucumber or BDD, a tester or developer has to write short description of what does the cucumber, when we read this sentence in cucumber, what should we actually execute? So that part, I think, is not automatic here. So the final step to make it a concrete test case still has to happen by hand. Yes, you see here in the abstract. Then testers write cucumber mapping, so that's what it's called in BDD, for these generated scenarios. Skyfire does not only generate effective tests, but it's also completely compatible with the existing agile development and continuous integration rhythm. Okay, interesting. So here they present an MBT tool called Skyfire, which integrates with Cucumber. It reads, yeah, we already said this. The generated test consists of identifiable elements, transitions and constraints from the diagram, right? And it converts these tests into cucumber scenarios. The practitioners leverage the mapping mechanism of cucumber, so existing ways of expressing that mapping from high-level test steps to the test code to create the mapping from model to concrete test. To the best of our knowledge, this is the first time MBT is used to generate test scenarios for cucumbers. So it's an interesting technique here, right? So why did they do this? So they describe 4 problems that prevent practitioners from adopting some of the previous MBT techniques. So this is important for you, not only for this paper. I think this has important information for you in general for this course. So first, the first reason out of 4. The first, previous MBT techniques often use complicated approaches with multiple models. Yes, this is a problem. Models usually include lots of additional information used for transforming abstract test to concrete test. This is true. So often you write your models in some specific language. You need to learn the language. You need to encode your models in this language. So imagine if you're a company and you have already lots of code which is not modeled in this language. Then you will have to create the models to then be able to run tests based on those models, right? So they give an example, Briand and Labiche. So Briand is a famous researcher in this field, used supporting UML models, i.e. IG, use case diagrams and class diagrams to provide the additional information in their totem system, which assumes the existence of artifacts that are not always available. So this is not, I'm not blaming Briand and Labiche. This is a thing of a lot of the model-based testing research, is that they assume that you already have the models in the correct form. But of course, for a company, this would be a major cost. And they describe some other approaches. Yeah, so the end thing is that this makes model creation difficult and costly. And it distracts practitioners from focusing on system behavior. So that was the first problem they saw with the existing MBT area. So second problem, previous MBT techniques have their own mapping mechanism from abstract test to concrete test. Yes, so here again, when you need to map, So first thing is that you need to have the model. Second one is that you need to learn this language, and how are you going to map the abstract things expressed in the model to more concrete test cases, right? And so this can be a steep learning curve, and you need to learn new tools and techniques. Third problem, previous MBT techniques usually provide language and platform specific solution when generating concrete tests. Yes, so it's typically you buy TTCN because you're in a certain domain and you work with certain types of languages. Or if you are in a different domain, you need to find another tool. And there's no sort of, there's often the tooling is different. So if you use UML, it has a different way of describing the models. So adopting these MBT techniques into a different language or platform requires great effort, making practitioners reluctant to use them. This is true. This is something we've seen in practice. And the fourth reason is that previous MBT research tools may not be compatible with industrial agile development and CE environments. So there's a mismatch here. This paper is a few years old now. But for sure, these four reasons are important for you to understand, because this is a limitation for many tools in MBT. So, of course, if you've already invested heavily in modeling in your company, you should try to find a model-based tool that maps to these models, or that you somehow can transform your existing models into one of these tools. But still, if you can transform, you still need to work with the model for that tool, right? So you still have that learning curve. So here they try to address this by using more sort of modern or commonly nowadays used technologies, like maybe Cucumber, right? I mean, it can be something else, but the general idea. So they read in a model, they convert that into graphs, some kind of internal model, and then they generate abstract test cases, test paths in this model. And for that, you need to specify some graph coverage criteria, like we have discussed in the course. Then they generate abstract test cases, and then they transform that to Cucumber, right? So this is basically the overview. And they compare this with some manual testing. I mean, we don't need to go into the details here. We understand the basics of it. They say it's better, but that depends, of course, on your situation. They say, second, unlike manual written steps, Skyfire generates clear steps for practitioners to map. Okay, maybe. When checking step definitions mappings for the manual written scenarios, we found that some step definition mismap because of the steps are long and look similar. So, okay, maybe there's some benefit here. But important to example here. So finally, just to see what kind of domains and how does it divide between domains. So model-based testing for software safety. So here's a specific, this paper is a little bit more focused on safety. You don't need to read this in detail, but I want you to at least seen this. There's focus on automotive, on railway systems, right? And then increasingly on robotics. There's less in medical, in power, in nuclear, and so on. So automotive, so that's why you see Germany a lot. You see railway, you see the French and the Canadians, and so on. So just to give you a sense. Okay. What kind of motive did the existing research give for introducing model-based testing? So 13 of the ones they studied here, I mean, you can just see the relative here. Improving test coverage. So they claim that they go with model-based testing because it allows you to basically have coverage criteria and be more sure that you've covered interesting cases. Second reason given was reducing cost and development time. And then the third reason was to increase the fault detection. And fourth reason was improving test efficiency. So we've already discussed this previous lectures and modules. The type of thing being generated, so it's often a test case, right? Can be test sequence is a little bit more abstract. Test data, I would say, is on the rise. So you see more and more tools focusing on test data, and then you have a few others with little focus on test oracles. Okay, that's it for today, and I'll add one example a recent example, advanced one on UML based model based testing in UML setting. But then we'll go on to property based testing in the last few modules of the course. Thank you.